Hello, everyone. I'm Forrest Eckhart.
And I'm Sophie Wigmore.
We're a pair of engineers working at VMware on Paketo Buildpacks as part of a Bill of Materials initiative. We'd like to talk to you a little bit today about how we feel that could be super beneficial to your software development process. Let's start out with talking about what Paketo is. Paketo is an implementation of Cloud Native Buildpacks. Cloud Native Buildpacks themselves can be thought of as an extension of the original Cloud Foundry Buildpacks with an aim on making it more accessible to the cloud native space. So taking your source code, turning it into OCI images, which are compatible with cloud native platforms such as Kubernetes. With that, you get a whole host of advantages like you would get from the Cloud Foundry Buildpacks, such as reduced configuration overhead, quick operating system patching, and reproducible builds. If you want to see a full list of features, you can check them out at buildpacks.io/features. However, today we're going to be talking about the native solution for auditing your container, dependencies, and packages via the bill of materials. So let's talk about why you would want to be worried about a bill of materials. Say you're an app developer. You're most likely using open source software, which is great because you can take pieces of software, plug them in, and use the power of code that's been developed by hundreds, if not thousands of people to quickly build out a featureful app. This might be an example of your dependency tree for your application. Now, in reality, you're probably using some complex dependencies, which themselves have some dependencies, which we can see in a graph like this. Now, those might also have some dependencies as well. So we could keep going on and on, deeper and deeper. But this is a pretty good representation for this demonstration. This is great and all, but open source software can become susceptible to any number of vulnerabilities. And when that happens, you poison all the way up the chain. And now not only is this a problem for this single app instance, but for all of your app instances that are running off of this image. We don't have to go back very far to find examples of where these kind of supply chain attacks have been absolutely devastating. It's also worth noting that these vulnerabilities that can cause these kind of supply chain failures are omnipresent. According to NIST's National Vulnerability Database, which is a catalog of over 160,000 vulnerabilities, there are over 12,000 of those that are considered critical and upwards of 50,000 considered high or critical. If any one of your dependencies is susceptible to one of the vulnerabilities outlined in the critical or high to critical, your entire application with that entire supply chain is vulnerable to attack. Now you might be thinking, well, that's not too scary because in your example at the beginning, I can see the little red node at the end and I can go in and either remove it or patch it. It's not really how it looks in the real world. It looks more like this in the real world. An opaque application image with no way to know what packages, version of packages, or any other information about it other than maybe what the app inside of it is. And so you have no way of knowing if you're vulnerable or not by just looking at this app image. So how do you get a more transparent view of your application? That's where something like a bill of materials can come in handy. A bill of materials, since I've been throwing that term around a lot, let me actually define it for you, is a formatted file with a list of all of the packages or dependencies that an application uses. On the left, you can see that we have a small little toy example to play around with. And there we have some information like the name of the package, the version, the SHA, the URI. And then we have two special fields, licenses, which are a specially formatted field in most bill of materials, and then vulnerability identifiers. These are pieces of information that allow you to identify a package inside of a vulnerability database to see whether or not that package is vulnerable. Here we have a couple of examples, CPEs, which are these common platform enumerators, which is used by NVD currently. SWIDs, which are the software identification tags, which NVD is planning on moving to in the future. And these PURLs or PURLs, which are package URLs, which are a way for you to identify the exact package that has been installed in URL format. Currently, bill of materials is used mostly by the medical and financial technology industry. However, there has been a big push recently to make it more widely adopted by everyone who's doing software. There are a couple industry standard schemas that I also want to bring up as well. We have CycloneDX, which we will be talking about later in this presentation. That is a schema that is backed by OWASP, and SPDX, which is a schema backed by the Linux Foundation. Great, I have a bill of materials. How does this help me at all? Well, you have a bill of materials, so you now have a complete catalog of the packages that your application is using. With that catalog, you can feed that into tools that allow you to scan for vulnerabilities. Here we have a couple of examples of those kind of tools, such as dependency track, scan OSS, and Gray. These tools will take in bill of materials, scan the packages inside of them, look to see if any of them are vulnerable, and if they are, let you know about them, and in some cases, even give you mitigation or patching strategies. We get a solid chain of custody. You actually know what's in your application, which is nice because you don't necessarily always know, as I pointed out earlier. And with that special license field, you're able to see the licenses of packages and evaluate them, which is critical for speeding up your compliance process for those of you that have tricky compliance issues. Now, let's get into a real world example to help visualize what this actually looks like. We'll be using a tool called Syft, which is a bill of materials generator, and we'll be scanning an application generated using Pack. Pack is a tool that takes in cloud native build packs and application source code and generates an OCI image. So Syft was scanned on an OCI image that was generated by a Pack building an Maven app using Paketo Java Buildpack. We asked for the bill of materials to be in CycloneDX format. So let's get an example of that. On the right, you have some parsed CycloneDX. We parsed it for you because it's actually several tens of thousands of lines of XML, and we figured that this would probably be more digestible. But let's walk through some of the interesting features of this file. So first of all, we have the identification of the application itself with the name, Maven app, a version, which in this case is actually an image digest, and a type, which is a container because we were scanning an image. Next, we have the components. You can think of these as all of the packages and dependencies that your application has. For this app, we have two really versions of that, which are Maven packages and Debian packages. So for the Maven packages, right here we have HDR histogram. You can see we have the name, we have the version, we have that PURL that I was talking about earlier, which identifies that it's actually a Maven package, and it actually shows you its sort of originator. And then it tells you what type it is. So it's a library. And then we have add user, which is a Debian package. We have the name, the version, that same PURL, and the type, which is again, a library. Now, with that, and with that sort of rudimentary knowledge of what bill of materials look like, I'm gonna hand it over to Sophie to talk more about what Paketo is doing with bill of materials.
Thank you so much for that, Forrest. Yeah, let's take a little bit of a look at what the Paketo bill of materials currently provides. So we access the bill of materials via Pack. And as Forrest said, Pack is a CLI that allows you to build containers using Buildpacks. So we generate our bill of materials using Pack by running the pack inspect BOM command on the same Maven app image that we used in that Syft example. The bill of materials is already natively a part of your container image created by Pack. So we have the added benefit of having no associated generation time when you are retrieving the bill of materials for your app image. First and foremost, over here on the left, we have an array of dependencies installed by Maven. So as you can see here, there are 49 dependencies, the first of which being HDR histogram, the same entry that we saw in the Syft example. So this list of 49 entries is essentially a one-to-one mapping with all of the Maven installed modules that we saw in the Syft example. Right now, this only has a SHA and a version field on it, but eventually we'd like to flesh this out to include vulnerability identifiers like CPEs, licenses, source URIs, and other information. Next, in the same bill of materials, you can see an entry for a dependency called the JRE, and there's a few other dependencies here. all of the dependencies in this section are representative of dependencies that are installed by our build packs. So JRE, the JVM kill agent, and Spring Cloud bindings are all examples of things that are installed directly by our build packs. These include a lot of information about licenses, stacks, SHAs, versions, and Syft didn't find these entries. This is because the build packs put them in non-generic file system locations, the layers directory, and therefore Syft didn't know to look in these directories. If you have a container with any dependencies that are outside of the standard location on your file system, any scanning tool may or may not be able to pick up on them. The final leg of our bill of materials is the stack bill of materials. So the stack image for us is a fancy name for the base image. So this is responsible for providing the base operating system for the container. Therefore, the associated bill of materials here contains all of our operating system level packages. As you can see, there are 96 of them, and the first one being add user. So these entries, again, are more or less a one-to-one mapping with the operating system level packages that we saw with Syft. We currently grab this information using a Docker inspect command and then looking at the IO Paketo stack packages label. Eventually, we'd like for this to be consistent with the bill of materials from the slide before and then merge together with that bill of materials from the previous slide and accessible via pack rather than using a separate Docker inspect command. So we've talked a big game and mentioned one or two differences in our bill of materials compared to the bill of materials from other tools. But I think that our bill of materials is special in another way, which is best explained by an example from the movie Ratatouille. So in the movie Ratatouille, we have Anton Ego, the food critic. He tastes the ratatouille dish, and let's say he makes his best guess at all of the ingredients that are in the dish. Even if he's really, really good at his job, he can pick out most of the ingredients in the dish. There's still a chance he wouldn't know every single ingredient, and he definitely wouldn't know where the ingredients were sourced from or what order they were added in. On the other hand, we have Remy the rat, the chef creating the dish. He has the exact ingredients in front of him while he's making it, and the list of ingredients is generated incrementally as he makes the meal, and there's no way that he could miss something because he's literally the orchestrator adding everything in. Either option here could probably give you pretty good insight into what's inside of the dish, but if you had a life-threatening allergy, you might opt for Remy's ingredient list because it was created natively as a part of the cooking process. That's kind of how you can think of our bill of materials versus the bill of materials generated by other tools. Instead of a life-threatening allergy, let's say it's your application secure software supply chain at stake. And the tools out there are represented by Anton Ego in this case, because they can get most of your dependencies and packages from the bill of materials just by scanning the image after it gets created. In this scenario, build pack bill of materials is represented by Remy because we gather the entries natively during the build process itself and have a bit more insight into everything beyond just what you can see in the final app image. The thing that sets our bill of materials apart is that we can collect the dependencies for the bill of materials as they're involved in the process. So how is this different, or how is this difference important or helpful? Well, bringing it back to our earlier example that Forrest had touched on, when you look at this bird's eye view of all of the dependencies in our final app image, still not representative of the whole picture. This represents the complex web dependencies just in your final app image. There's a whole extra set of dependencies that are involved in the build process of your app image, but they get cleaned up afterwards to keep your final app image slim. This is part of what makes Buildpacks really great because all of this is taken care of for you, but not all scanning tools can pick up these dependencies that went into the making of your app image, especially if they're not present on that final app image. Including this information in the bill of materials provides a bit more of an informed view of the dependency tree involved in your bill of materials or involved in your app image. So the final product that we're trying to provide here is a very consistent bill of materials across your build image, your final run image, and the base operating system image. Then this bill of materials should be consumable by any downstream supply chain analysis tools for your use. Finally, this experience must sound great and has a lot of value added potential, but not all of these things are currently present in the bill of materials example that I showed you before. This is because they are a work in progress. First and foremost, we are creating a robust build time dependency bill of materials, and it's one of our top initiatives in our Paketo project. This metadata isn't currently available, and we're currently whipping it up right now with the goal of having all of these dependencies documented with licenses, CPEs, or other vulnerability identifiers, SHAs, URIs, and any other relevant metadata that we can gather. And we're also collaborating with the upstream Cloud Native Buildpacks project about how we can make that information more available from the Buildpacks. Another work in progress that we have here right now is an effort to standardize the output of the bill of materials to an industry standard format. For example, Forrest mentioned SPDX and CycloneDX as two possible formats, and we are currently leaning towards CycloneDX for our use case, but we're making these decisions and discussing the alternatives through a public-facing RFC process. So we'd love to hear from any potential users or anybody who's interested in about what they'd like to see here. Buildpacks are constantly trying to improve the information that they can provide to users to the bill of materials. And this information will only become more robust and refined as the Buildpacks themselves mature. Our work with the Buildpacks bill of materials is only just getting started, and I hope from this presentation you can get a sense of what we're trying to accomplish. Thank you so much for listening, and if you want to get in touch with us, you can reach us on Slack, via GitHub, or at our weekly working group meeting. And you can also check out the RFCs that I mentioned during the presentation if you want to get involved and chat with us about the way that we want to build our bill of materials. And we can take some questions.